In addition to the possibility of spatial problems caused by vestibular or visual illusions, spatial misperceptions can also occur when pilots transition their view from an outside perspective to heads-down instrument displays. Among the types of spatial disorientation problems associated with outside-to-inside transitions, control reversal error has been identified as a relatively common and potentially dangerous occurrence. To help recognize and avoid this potentially dangerous cognitive threat, enabling objectives presented over the course of this training module are designed to help pilots identify the definition and causes of control reversal error, define how spatial strategy conflicts and the Leans illusion increase risk of spatial disorientation, and identify how to recognize and avoid problems associated with control reversal error. On a warm, overcast evening with calm winds punctuated by an occasional rain shower, the captain of a commercial Boeing 737-800 airliner released his brakes and advanced the throttles forward to initiate takeoff roll. 15 seconds later, as the aircraft reached its designated rotate speed, pilot eased back on the control column, lifting the 76-ton plane into the air. Once airborne with 114 souls on board, the aircraft continued to gain airspeed and altitude. However, instead of remaining wings level with a slight nose-up pitch, the aircraft angle of bank slowly increased with an uncommanded right roll. The captain immediately perceived the unexpected rolling motion and accordingly nudged the control wheel leftward to correct for the unintended bank. The aircraft quickly responded by returning to an acceptable 3-degree roll limit as the flight continued gaining altitude. Passing through 1,000 feet, the captain called for autopilot selection and simultaneously ceased his active control inputs. Unfortunately, neither the captain nor co-pilot verified autopilot activation, which, contrary to the flight's crew perceptions, had not become engaged. Without autopilot guidance or manual inputs from the crew, the aircraft continued to climb for 55 seconds, during which time the plane's right roll tendency resumed, causing the angle of bank to gradually increase. For almost a full minute, the flight crew had become preoccupied with the weather radar and new heading altitude selections, and failed to notice the deteriorating flight parameters that were clearly displayed on the respective instrument panels. After passing through 2,500 feet, the undetected roll exceeded established 35-degree safety limits and subsequently caused onboard sensors to trigger an audible cockpit bank angle warning alarm. With initial sounding of the alarm, the startled captain immediately resumed active wheel inputs. However, in his rush to analyze their situation, he apparently became confused with the attitude director instrument and mistakenly increased their bank angle by rotating the wheel 22 degrees rightward. Recognizing the aircraft roll direction was increasing rather than leveling out, he corrected his error by rapidly reversing the wheel position to 20 degrees left. This action seemed to further confound his spatial awareness as he quickly responded with another 45-degree right control input. Unfortunately, this series of rapid and confused control movements had the cumulative effect of extending the airliner's unintended right roll from a relatively benign 35 degrees to a potentially dangerous 50-degree bank angle. Recognizing that his control efforts were not helping their situation, the captain hastily switched on the autopilot, which on this attempt successfully engaged and prevented the aircraft attitude from further deteriorating. For the following 5 seconds, no control inputs were made by either pilot as the airline continued climbing at 180 knots with a steady 50-degree right bank and a nose elevation of 5 degrees. After 5 seconds of stable flight, the captain resumed active control of the aircraft and began making intense wheel movements that forced disengagement of the autopilot. Unfortunately, his inputs continued to worsen their situation as he repeatedly jerked the control wheel right and left in rapid succession. With the right roll reaching 70 degrees and the nose dropping through the horizon, the co-pilot made a desperate attempt to spatially reorient the captain. 2 seconds after the co-pilot's plea to correct left, the aircraft nose fell to 20 degrees below the horizon, and the aircraft became inverted with a bank of 115 degrees. 5 seconds later, the aircraft impacted a level uninhabited mangrove swamp with an airspeed of 287 knots and 60 degrees of right bank. Several days after the crash, the National Transportation Safety Board began an investigation to determine the mishap causal factors and to also identify what actions could be implemented to prevent future accidents of this type. Based upon the flight data recorder information recovered from the mishap site, the investigation team concluded the airplane crashed after loss of control by the crew as a result of spatial disorientation. The investigation board also determined that when the captain grabbed the controls to recover from the uncommanded roll, he appeared to be confused about the attitude of the aircraft and subsequently began to make erratic control inputs that worsened their situation. The captain's incorrect control inputs seemed to compound his confusion, and despite having a large, fully operational attitude display directly in front of him, he continued to make rapid and repetitive control reversal errors, which caused the aircraft to enter a spiral dive that ended when they struck the ground with 48 degrees of nose-down pitch and 287 knots of airspeed. The control reversal error that occurred with the 737 mishap flight is a common form of disorientation characterized as a cognitive processing problem that is most often associated with switching between outside and inside spatial strategies. A control reversal error event becomes apparent when a pilot executes a control input that results in aircraft roll or pitch opposite to what was intended. Scientists evaluating this type of disorientation have found that during relatively easy transitions, these errors occur about 7% of the time. However, during more difficult out-to-in transitions involving formation flying or unusual attitude recovery, control reversal error rates may be as high as 50%. During the early 1930s, moving horizon ADIs became standard equipment in both U.S. military and most commercial aircraft. However, there were initially some design controversies regarding whether it might be better to have the aircraft symbol move rather than the horizon bar. Recognized experts at the time insisted that the moving horizon displays were superior because the moving horizon instrument displayed, in their words, exactly what we would see if we looked at the real horizon through a small window. These same experts explained that moving horizon instruments displayed to the pilot what they thought was a normal picture. Unfortunately, the belief that moving horizon ADIs accurately represent a pilot's outside view has turned out to be an incorrect assumption. In the early 1990s, researchers discovered when pilots look outside the aircraft during turn and bank maneuvers, they reflexively tilt their heads toward the horizon instead of maintaining head alignment with the cockpit vertical axis. If we examine the following gun camera video, it's easy to understand why display designers originally misinterpreted how pilots perceive outside visual references, since the camera's fixed point of view clearly shows cockpit images that appear stable as the outside horizon seems to be in motion. However, if you carefully observe the pilot's head movements in the top video, you will notice that unlike the gun camera that is fixed in the cockpit, the pilot's head tilts toward the horizon as the aircraft angle of bank increases. This recently identified head tilt response, known formally as the optokinetic cervical reflex, or OKCR, is thought to aid pilot spatial awareness by keeping the outside cockpit view stable on the retina, while peripheral views of the glare shield or other airframe parts are perceived as being in motion. This visual perspective provides a distinct advantage for enhancement of pilot spatial awareness, because visual feedback created by peripheral views of the glare shield, canopy bow, or wingtips will move on the retina in the same direction as the stick control inputs. In contrast, the ADI's relatively small artificial horizon is insufficient to trigger an OKCR head tilt response, which means during instrument flight, an aviator's head will remain aligned with the cockpit, which consequently causes the ADI horizon symbol to be perceived as an object in motion. Added to this outside-inside transition disparity is the fact that using an inside moving horizon fixed cockpit spatial strategy will create loss of compatibility between control motion and visual feedback, since the artificial horizon symbol will always move in a direction opposite to the stick control movements. When transitioning from an outside view to heads-down instruments, the reversal of motion between stick input and horizon symbology is known to cause momentary confusion and disorientation that can lead to control reversal error. In addition to reversing spatial strategies during transition from outside to inside references, sudden activation of the vestibular system also occurs when pilots reflexively realign their heads with the cockpit. As a pilot's head moves back toward the cockpit vertical axis during instrument transition, the semicircular canals will become stimulated even though the aircraft may be holding a constant angle of bank. In this situation, activation of the vestibular system creates what is known as intravestibular conflict, which is a condition known to cause confusing motion signals capable of inducing control reversal error and can also create another common spatial misperception known as the leans. The leans illusion is the most common form of spatial disorientation, and many aviators have experienced this spatial misperception on multiple occasions. This illusion, which is typically characterized as a false sensation of aircraft bank, usually occurs within a few seconds of rolling wings level following completion of an extended bank turn. Although the leans is not generally considered a severe spatial disorientation problem, in high workload situations similar to what the mishap 737 crew encountered, the leans may introduce a significant distraction that may increase the risk of committing control reversal errors. The basic etiology of the leans revolves around the fact that during a coordinated heads-down turn, pilots will usually perceive their up and down gravitational axis as being aligned with the vertical axis of the cockpit rather than the Earth's gravitational force. This illusionary offset of the Earth's vertical alignment occurs in response to accelerations encountered during bank turns. As an aircraft increases its roll angle, the resultant centrifugal and Earth's gravitational forces combine to create an artificial gravity force vector perceived by the pilot as one unified force vertically aligned with the cockpit. This upright illusion is often reinforced by the semicircular canals within a pilot's vestibular system because during a sustained bank, sensory mechanisms within the canals will eventually become stabilized with the cockpit, and when combined with the centrifugal force, can provide the illusion of being upright while maintaining a sustained angle of bank. This false sensation of being wings level is caused in part by the roll sensors within the semicircular canals, which consist of small movable sensory hairs that make up a flap-like structure called the cupola. When pilots encounter any sort of angular head motion, such as that produced during roll maneuvers, fluid within the semicircular canals will flow in a direction opposite to the turn and thereby cause the cupola to become temporarily displaced. The displacement of these specialized sensory hairs is what generates roll sensations whenever a pilot enters or recovers from a bank turn. When aircraft roll angles are changing, a pilot's canal fluid will remain in motion and the bent cupola hairs will continue providing roll sensations. However, if the roll angle remains fixed for 20 seconds or more, the canal fluid will become stabilized and the cupola will return to its neutral position. If a fixed roll angle is maintained during a coordinated turn, in addition to sensations of the roll disappearing, the resultant centrifugal force can also make pilots feel as if the aircraft is level, particularly during IMC flight. This sensation of feeling level while holding a bank turn can generate problems with the leans when a pilot rolls out of the turn back towards a wings level attitude. The resulting vestibular stimulation signals to a pilot the aircraft is rolling out of the turn back toward level flight. However, since the original forces of the sustained turn provided a false upright sensation, the sensory stimulation generated during return to level flight can provide an illusion of overbanking beyond a wings level attitude. Although this false sensation of leaning or rolling in the opposite direction will usually last only a few seconds, a pilot that is not paying close attention to his instruments during roll recovery may have a tendency to unintentionally re-enter his original bank, since this action could again regenerate the illusion of being upright with the Earth. In order to minimize incidences of the leans during a sustained bank that involves flying in and out of clouds, pilots should consider remaining on instruments during VMC or breakout portions of the turn. By using this approach, off-axis head movements will be minimized and thereby reduce the potential for intravestibular conflict that could lead to sensations of the leans or air sickness. Also, avoiding unnecessary head movements while holding a fixed bank angle will reduce semicircular canal stimulation and thereby reduce some of the risks associated with intravestibular conflict. Flight crews should remember that after completing a roll recovery, fluid in the semicircular canals will remain in motion for at least 10 to 20 seconds, during which time pilots may experience false sensations of bank that can generate the leans. If leans illusion persists after returning to wings level, further flight maneuvers should be avoided for 30 to 60 seconds or until false sensations of bank have dissipated. To help alleviate any sensations of disorientation, including the leans, pilots should always cross-check their artificial horizon display after completing a roll recovery or when attempting to hold a fixed angle of bank. The flight data recorder information recovered from the 737 accident suggests it's quite possible that both control reversal error and the leans illusion contributed to this mishap. During the takeoff and initial climb-out, the captain, who was the pilot at the controls, was initially using an outside spatial strategy prior to calling for autopilot initiation. After passing through 1,000 feet, 30 seconds after takeoff, the captain ceased making control inputs because he assumed incorrectly that the autopilot had successfully engaged and was keeping the aircraft on course. Rather than monitoring the attitude instruments, both the captain and co-pilot had shifted their attention to the center cockpit weather radar screen, and they were also occupied with making inputs to the navigational computer system. For the next 55 seconds, neither pilot used any active spatial strategy to orient the aircraft, since both believed the autopilot was engaged. During this 55-second period, both pilots failed to adequately monitor the attitude instruments during this critical phase of flight. Subsequently, the aircraft's uncommanded right roll remained undetected until it reached the maximum safe bank angle of 35 degrees. Once the unintended roll reached this critical point, the bank warning signal suddenly activated in the cockpit. With the loud sound of the bank angle alarm, the startled captain, who had been preoccupied with the navigational system, attempted to make an instant determination of the aircraft attitude as he simultaneously began making roll control inputs. Unfortunately, as soon as the captain began his roll recovery attempt, he had to contend with 3 human factor issues known to increase risk of control reversal error. He was already dealing with a high mental workload, and now he was suddenly forced to make a rapid transition to instruments while simultaneously activating his vestibular system as he turned his head from the weather radar screen to the ADI located in front of the control column. His final wheel input error caused the roll angle to exceed 90 degrees of right bank, which caused the aircraft to become inverted with the nose pitch angle falling below the horizon. The aircraft then entered a steep inverted spiraling dive that quickly ended with catastrophic ground impact less than 30 seconds after the captain made the first of his 5 control reversal errors. To help prevent control reversal errors similar to what was experienced by the captain of the 737 mishap aircraft, pilots as well as other cockpit flight crew members should be able to recognize the conditions that can induce this type of spatial disorientation. Cockpit crews should be able to recognize the early onset of control reversals and should be familiar with the countermeasures used to overcome the spatial perceptual problems associated with this type of error. The conditions most likely to cause control reversal error are those that involve either switching from an outside to inside spatial strategy or, as the case of the 737 captain, suddenly and unexpectedly switching from a non-flying cockpit task to hands-on instrument flight. In situations where a pilot with a high mental workload must suddenly take control of an aircraft that is already in an unexpected roll or pitch configuration, the risk for committing control reversal error may be substantially increased. If a sudden transition does trigger a few small incorrect stick inputs followed by rapid control corrections, it usually indicates the pilot has recovered from an episode of momentary confusion with the ADI spatial information. However, in cases where control reversal errors do not dampen out and instead begin to increase in magnitude, it indicates a pilot is becoming more disoriented with respect to which direction the controls should be moved. Flight crews should also remain aware that during transitions between outside and inside perspectives, the pilot's peripheral view of the cockpit will suddenly become stationary as his view of the artificial horizon begins to move. The sudden switch between outside and inside perspectives requires pilots to instantly reverse their orientation strategy from a fixed horizon moving cockpit to a moving horizon fixed cockpit perspective. In conjunction with this reversal of spatial cues, outside to inside transitions force pilots to lose sensory spatial compatibility between stick control motions and visual feedback. Further complicating the situation is the fact that realignment of the head with the cockpit vertical axis will also cause intravestibular conflict that can further increase the risk of spatial disorientation. Fortunately, once a pilot has successfully transitioned from outside visual cues to inside instruments, Aeromedical researchers have been able to document there will usually be no further risk of control errors, since it is the point of transition that brings about the reversal of spatial cues with the inherent risk of disorientation. For this reason, it is imperative to transition early whenever possible, since studies conducted by the FAA indicate it may take up to 30 seconds to fully switch from an outside to inside spatial strategy. Also, once a heads-down transition has been successfully accomplished, a pilot should not attempt to repeatedly cycle between outside and inside spatial perspectives, since this type of behavior will greatly increase control reversal error risk. In multi-piloted aircraft, one of the most effective methods for resolving a suspected spatial disorientation problem is to notify the crew of a potential problem and then having the non-flying pilot take over control of the aircraft. However, in situations where both pilots may be disoriented or in single-piloted aircraft, switching on the autopilot to stabilize the situation has been shown to be an effective way to allow time to regain spatial awareness and to then apply an effective spatial strategy. Also, a common method for coping with control reversal error is to remember when transitioning to an artificial horizon display, bank direction is indicated by the portion of the aircraft symbol that overlaps the dark part of the moving horizon ball. For some pilots, thinking of this as the wing in the dirt seems to minimize confusion with interpreting ADI symbology motion and may help resolve problems with control reversal error.